Eulerian graphs have a circuit that covers every edge. Question I asked at the end of Friday, what if I don't care about the edges, and instead care about the vertices? On page 141 in the textbook is a picture of a museum. I don't know who built this museum. There's not a freaking square corner in the entire damn place, and that was an architect's nightmare, but here's the museum. Can you visit each room exactly once, starting and ending in the reception room? Maybe. My first problem is I hate this. This map is atrocious. So let's cheat and turn each room into a vertex and each door into an edge between corresponding vertices. And then I have this instead. Each room is still numbered exactly the same, and the doors have just become the edges. Can you walk through each and every room exactly once, starting and ending in room 1? Maybe. If you're sure of it, you should write it down. Write down a path. There are lots of them. Now I'm going to cheat. Look, there's one. So yes, the book tells me I can do this. Starting and ending in room 1. 1 to 2 to 4 to 9 to 13 to 14 to 10 to 5. There it is, laid out for me, one after the other. Clearly, I can't go through every door once because I have rooms with odd degree. So there's not an Eulerian circuit in this graph, but there is a tour that takes me through every vertex. All right, wait a second. Doesn't repeat a vertex. So it can't repeat an edge, can it? That makes it not just a circuit, but a cycle. I'm going to call such a spanning cycle a Hamiltonian cycle. No, it doesn't have to have anything to do with missing a shot or anything like that. Wrong Hamilton. And such a graph that contains such a cycle, is a Hamiltonian graph. Name me any Hamiltonian graph. There are whole categories which we know are Hamiltonian. Any cycle, as a matter of fact, as long as it has more than 2 vertices. Because if it only had 2, we'd have to go back and forth over the same edge. Don't want to do that. But if I have 3, I can just go around the loop. So absolutely, any cycle is Hamiltonian. And therefore, any other graph on n vertices that contains a cycle Cn. Right? The only one I can guarantee you also contains Cn is the complete graph, because then it connects all the things that are distance 1 and distance 2 and distance 3, right? On the other hand, a path I can't get back on. But just like I had in Eulerian terms, I had an Eulerian trail that would go from one vertex to another, I can have a Hamiltonian path. It's going to go through every vertex, starting at one and ending at another. Clearly, if I have a cycle, I have a path. Why? I'm asking you for proof, but not formally. Yeah, a cycle is a closed path. So if I want a path, I just don't close it, right? I go to the last penultimate vertex and then stop there. So I go all the way around, and it's about to close the cycle. I stop at the vertex before the end. Gesundheit. What's the graph K33? They connect to each one. I need you to be a little more precise there. The bipartite graph. Every vertex in the 3 on the left connects to every vertex in the 3 on the right. There are no connections on the left between and no connections on the right between, which means this graph looks like this. Right. That's Hamiltonian? Is it obvious to you that that's Hamiltonian? But a Hamiltonian graph is a cycle that contains every vertex. I need you to step up from path to cycle, which means there should be a C6 in here, right? Label time. I would really like to see the cycle C6. I'm going to cheat. I want you to take A2 and B2 and switch their sides. Don't change the graph's connections. But I want you to redraw this with A2 way over here on the right and B2 way over there on the left. So I'm going to pre-label my vertices. My vertices are A1, B1, B2 on the left, A2 on the right, A3 on the left, B3 on the right. And now make the same connections. Connect all of the A's to all of the B's. Connect all of the B's to all of the A's. Do not connect any B's together. Do not connect any A's together. Wait a minute. I'm supposed to connect the A's to the B's, right? So I'm going to connect A1 to B1, B2, and B3. I'm going to connect A2 to B1, B2, and B3. Son of, there it is. A3 connects to B1, B2, and B3. There's my C6. Now, Jonah, where is that in the original picture? That's now the question. There's my cycle going around my A's, right? A's and B's around the outside here. Okay, wait a minute. I go from A1 to B1, then to A2, then to B3, then to A3, then to B2, then back to A1. It's kind of hard to see up on the top. A lot easier down here. This is a problem. Figuring out where my cycle is. And what that really means is that K33 is C6 with a couple extra edges added. And that's why I could use Kn, because a complete graph is a cycle with a whole crap ton of extra edges added. I would hope so. It would be really nice if I could find a nice short algorithm to do that. Every vertex in this graph has what degree? Okay. If any vertex has degree 2, what do you know about those edges? Absolutely. Now that actually helps me even more. Here's another graph. Page 142. Six, 2, 4, 2, 4, 2, 4. Okay, good. Notice this graph is Eulerian. Vertices are either degree 2, 4, or 6. They're all even. I could, if I really wanted to, go across each edge once. Is this graph Hamiltonian? Ah. All right, wait a second. Reese, you said if a vertex is degree 2, then both edges that are part adjacent, incident, have to be part of the cycle. Where are my vertices degree 2? But wait, there's more. V and X and T, right? Which means I need all of the edges connected to T and V and X. I need to use this edge, this edge, this edge, but I also need to use VZ, XZ, and TZ. Wait a minute. That means I'm going to use XZ. Then I'm going to use Z to one of the others. And then at some point, I'm going to have to come back. I'm going to hit Z twice, aren't I? I can't have 3 edges incident to Z in a cycle. A cycle is 2 regular. Z has to be of degree 3. Not going to work. This graph is not Hamiltonian. Well, that's annoying as hell. But it's a nice way to figure out that something isn't Hamiltonian. Questions? Hmm. Here's my Peterson graph. Three regular. So none of these vertices are degree 2. No edges are forced to be part of a cycle. The textbook labels these by outer ring and inner ring. It labels the outer 5, U1 through U5. Clockwise. And it labels the inner ones as V1 through V5, also clockwise, starting from the top. Abigail, you were drawing in the air in front of you. Trying to make a cycle? Yeah. Okay. What'd you come up with? Did you make a cycle? No. Ah. Aha. Okay, Jonah, this is the problem part. I don't know if this is Hamiltonian or not off the top of my head. So let me just start looking at whatever cycles I can find. And then we'll go from there. A question for you. What is the smallest cycle you can find in this graph? I see 5s, yeah. Around the outside, the star in the middle, those are both cycles of length 5. Are there any squares in this graph? Are there any triangles in this graph? Ooh. Can you prove that? That's a really good question. Can you show there are never any cycles whose length is smaller than 5? If you were to do a cycle of length 3, there are only really 2 options. You either get 2 U's and a V, or 2 V's and a U. What's the problem with that? I would need 2 U's connected to the same V, and that doesn't happen. What if I wanted a quadrilateral? What if I wanted a cycle of length 4? Well, if that's 3 U's and 1 V, or 3 V's and 1 U, I run into the same problem. So the only way to do it is to do 2 and 2. So I need to do 2 U's and 2 V's. Which means I have to go UV, VU, right? Or VUUV. I can't go from U to V to U, because each V is only adjacent to 1 U. And I can't go from V to U to V, because each V is only adjacent to 1 U. So I've got to go UVVU. Where's my problem? Whatever U I pick is adjacent to some V. The V's that this V is adjacent to are not adjacent to either of the neighbors of that U. There are no triangles, there are no squares. The smallest possible cycle in here is length 5. As a matter of fact, we can go out and back, right? 1, 2, 3, 4, 5. I do a pentagon on the top. There are lots of cycles of length 5 in here, but there are no 4s and no 3s. Technically, I made this claim and then we discussed how to prove it. So I should write that as a theorem, but I'm not going to. That's enough. That turns out to be enough for me to say that the Peterson graph is not Hamiltonian. I wrote a theorem. I better prove this. If I want to prove something's not, this is going to be hard. So let's do it in proof by contradiction. Suppose it is. What do you know about that cycle? Yes. So how long is it? Give me a number. Yeah. Well, that's the only graph I'm talking about. PG. It's the Peterson graph. It's length 10. So I've got 10 edges, and I've got to get to every vertex, right? That means some or all or none of the edges that connect the outside and the inside must be part. If I don't have any of these 5 edges, I'm definitely not going to get all 10 vertices, right? If I miss UI, VI, I can never get from the outside to the inside or back. So I need at least some of them. If I have all of them, then I can only do 5 between the outside and the inside. But if I only have 5 edges between the 10 on the inside and the 10 on the outside, I can't get to everything and back. So I need some of these. So that means at least 5 of the edges, at least 5 of the edges are left. to distribute somewhere. Those edges either come from the cycle along the outside or from the cycle along the inside. I can't have all 5 of these. C must contain at least 5 edges from C prime, U1, U2, U3, U4, U5, U1, the outside cycle, or C double prime, V1, V2, V3, V4, V5, V1, the inside cycle. I'm going to distribute those 5 edges between 2 cycles. I can't do it evenly. It's either 3 and 2 or 4 and 1, right? It can't be 2.5 and 2.5. So without loss of generality, let's assume at least 3 of those edges are in C prime. Why do I know I can't contain all 5 of them? Why can I not contain all 5 of the edges in C prime? My Hamiltonian cycle can only hit each vertex once, so that whole C prime can't be a sub-cycle within it. I'd hit something twice. Same thing with C double prime. So it's either 4 and 1 or 3 and 2. So let's assume at least 3 of them are from here. That's really 2 choices, 3 and 2 or 4 and 1. Yes? So let's start with the idea that we have 4. But if I've got 4 edges on the outside, then I've got to connect to the inside somehow, yes? And I'm not allowed to use this edge. And I'm not allowed to use these edges, so I have to use those edges. But that's a cycle of length 8. Why is that a problem? I'm missing 2 vertices. I have to have a cycle of length 10 to have a Hamiltonian cycle. Crap. I can't have an 8 cycle and a 10 cycle in the same thing. Not going to work. I hit something twice. So I can't do it with 4. So let's do 3 on the outside. Okay, if I have 3 edges from C prime, 3 edges from C prime. If they were all next to each other, then I'd have a problem because I wouldn't be able to get to the outside vertex. If all 3 of the edges are connected to each other, how do I get to this one? Can't do it. I got to go from here, right? But how do I get here? I've got to go from here to here, and here to here, and then those go back down to those. Crap. I won't be able to get off of it. I'll end up with another 8 cycle, won't I? So these 3 edges can't be next to each other. Let's look at the right picture. 2 of them are connected, 1 of them is connected. They're not all adjacent to each other. That means I need to go from here in and here in. And that means I either have to go down, I can't go up, I'll get trapped. I go down, got to go out. I'm going to close the cycle of length 8 again, aren't I? Damn it. Or let's say I do go down here and then across and then up, then I have a 5 cycle. But I can't have a 5 cycle inside a 10 cycle. I'd hit something twice. No matter how I try and break these edges up to properly distribute them across my cycle, I never get it to work. Conclusion, there is no Hamiltonian cycle. Didn't bring it. I need a 12-sided die, and I forgot to bring one. A 12-sided die has pentagons for sides. 12 pentagons. By the way, they make calendars. Each month is on a side. You just turn the right side up. But that means that I can take a dodecahedron, a 12-sided die, and unfold it and lay it flat on a piece of paper. I did that. Technically, what I did is I took one of the pentagons and stretched it until it was flat. And that's the outside pentagon here. And I just laid everything down. This is called a net projection. This is a dodecahedron. Instead of making a calendar, I want you to imagine that this is a map of the world. Because it would be a globe if I pulled it back up, wouldn't it? In the late 1800s, I didn't write down the exact year, a game came out called the Icosian game. Icosian? On the map of the world, they labeled 20 cities. Count the vertices. There are 20 of them. And they gave you 20 little pegs and a piece of string. And they said, make a world tour. Find a tour that visits all 20 cities exactly once. Find a Hamiltonian cycle on this. Why was this any sort of reasonable sort of game to create? Because a certain book had come out fairly recently. Something about going around the world in 80 days. The game, by the way, flopped, did horrible, but it brought the idea of a Hamiltonian cycle to the public's attention, in spite of the fact that a gentleman by the name of Kirkman had actually asked about this thing years before Hamilton wrote a paper on it. So Hamiltonian cycles really should be Kirkman cycles. I don't get to make the rules. It's whoever wrote the most popular book, they get credit. Hamilton wrote a better book. By the way, you can. This graph is Hamiltonian. Your mission, should you choose to accept it, is to take a picture and decide if you can find a world tour. Jonah, I'm still kind of stuck. I don't have a good answer yet. How do I know whether or not a graph is Hamiltonian? Well, let's think about this for a minute. What do I know is true of Hamiltonian graphs? If my graph has a Hamiltonian cycle, it better be connected. Otherwise, there'd be a piece over here and a piece over there, and I can't get between the two. It's got to have at least 3 vertices. Otherwise, I'd have to go back and forth across the same. That's not working. That's not a cycle anymore. What else can't I have? That's a connected graph of order bigger than 3. But there's a problem there. Jonah? Got a cut vertex. If I have a cut vertex, then I have vertices that don't lie on a common cycle. And I want a Hamiltonian cycle. All the vertices should be on a common cycle. As a matter of fact, if I want every vertex to be on some common cycle, then I need my graph not just to be connected, I need it to be 2 connected. That means no cut vertex, means if I take 1 vertex away, my graph is still connected. If I take 2 vertices away, I might disconnect it. What if I take more vertices away? What if I take any cut set away, right? There's got to be some cut set that'll disconnect the vertex, the graph, or reduce it to trivial. There's got to be some cut set. All right, wait a second. I need some terminology explained to me. What? The hell is that? Oh, they actually look where the slash ends. It's a subset, but it's not the whole set. It must be a proper subset. And it can't be empty. So these two together mean a non-empty proper subset. Then what? Wait. Beg your pardon? What does that say? Edge connectivity is lambda. That's a K. Might just be my bad handwriting, but I'm pretty sure that's a K. And it's not a fancy K, which was vertex connectivity. So what the hell is this K? The number of components when I take away a cut set is smaller than the number of vertices I took away. My bow tie fails that, right? I take away one vertex, I get two components. This is a way to test if something is not Hamiltonian. What's the contrapositive of this statement? Street was a long time ago. Nope. Using this ever since.
If use Hamiltonian, then the amount of components and all less is the opposite of proper subset.
I think you've already made an error, because what I need to do when I do the contrapositive, I need to take the if and the then and reverse them. So the if part needs to be if my cut set is bigger than S. If my number of components is bigger than my cut set, then my graph will not be Hamiltonian. I'm getting warmer, Jonah. I've got a test for something to not be Hamiltonian. I just don't have a test for it to be Hamiltonian yet. More on this on Monday. I will see you all then. Have a wonderful day. The proof of this first theorem and the contraposition both are in the textbook. Ben. I need this. You need that. You used to have something for me.